Hello everyone and welcome back. Now, in the past few lectures, we have spoken a lot about how to solve differential equations. And in particular, we have focused a lot on linear, constant coefficient, second order differential equations. Remember, those are the ones that led to the characteristic polynomial. And we have a very nice and straightforward method of finding the fundamental set of solutions, right? It's just finding roots of that characteristic polynomial. Now, we've spent a long time burying our head in the theory. So what I want to do today is I want to do a little bit of application. And in particular, I want to focus on mechanical vibrations. So what I will do in this lecture is derive a second order linear constant coefficient differential equation that comes from a specific mechanical system to show you where these things might come up and how we can interpret the solutions. Now, let's go ahead and get started. The specific system that I want to look at is a very, very simple so-called spring mass system. So we imagine maybe we have something that we can anchor to. This might be maybe the roof or something along those lines. And we have a spring that's being pulled down off of this thing. And what's pulling it down is some mass that sits underneath it. So this mass is going to be m kilograms. And there's a few things that we should denote on this right away. First of all, we will let little l equal to the unstretched length of the spring. Okay, so if you just take, say, out of your pencil and look at your spring, you measure the length of that spring, that's going to be this little l. Now, of course, you could probably imagine what's happening here. If I put a mass on this thing and I just let it sort of hang there, it's going to stretch out the spring by some amount. Again, just take your spring from your pencil and pull it a little bit, right? And so in this case, we are going to use capital L to be the amount or the distance that the spring is being stretched by this mass that's hanging down here. Okay, so the first thing that we do when we derive mathematical equations is we go back to first principles. That means going all the way back to the physical forces that are acting upon this thing. Now, for the time being, I'm going to think of just the spring being stretched and pulled down by the mass. There is no dynamics here. This is a static system. That is, it doesn't change in time. So what I did is I hooked this thing up, and I put this mass on there. I let it go. I let it pull the spring down. I walked down to the room for maybe an hour or something, like everything settled down. I came back in, and everybody is in a nice static state of equilibrium. Well then, immediately, there is one force that we know is acting on this thing, and that is the force that's pulling the mass down. That is gravity. And in this case, we know from Newton's second law that the force due to gravity is just equal to mass times the gravitational constant of acceleration. So this is g, this is 9.8 meters per second squared. Now, if you think of how to do a free body diagram, we know that we need to have, in this case, if gravity is pulling us down, there has to be some equal and opposite force that is pulling us up. Again, this thing is in this state of equilibrium. It is standing there, so there's got to be something pulling us up as well. And you might remember from a physics class that that is actually going to be the spring tension, right? So the spring wants to be put together, right? It just can't fall forever, right? It's not like a piece of rope where if I put a mass on it, it would just fall until it hit the floor. The spring is pulling this thing back up. So we actually also have a spring force. And the spring force, in this case, is given by what's called Hooke's law. So I'm going to call this F sub s. Now, I'm talking about gravity going downwards, and I'm using that to be the positive direction. That means the spring force is acting upwards. I'm going to use that to be the negative direction, the opposite direction of gravity. That's all minus means here, okay? And in this case, we can use Hooke's law, which says that the force of this spring pulling us back up is proportional to the length that this thing has been stretched from its original length. So that is minus K times L. L is the amount that it's been stretched beyond its natural length. K is the proportionality here. So K is typically referred to as the spring constant. This is something that can be estimated from data. So if you were to sort of measure out this, this spring, we can actually find what this value is in the lab. But for our purposes, we are just going to call this thing K. It's a positive number. That's all that we care about for the time being. Now, at equilibrium, this thing is a perfect state of balance. So that means that at equilibrium, well, these two forces are equal to each other. They're balancing each other out. So it says that Fg plus Fs is equal to 0, which tells me that Mg and then minus KL is equal to 0. Now, what you can get from this equation, you can rearrange to isolate from L, which will tell you exactly how far the spring has been stretched. Or, as I said, if you build this in the lab, you can just pull out your ruler and measure what capital L is. We know what the mass is. Again, put this thing on a scale. We know the gravitational constant of acceleration. And this equation right here provides us with a method of finding K from a physical experiment, right? So even though K may feel a little bit inaccessible here, we just said it's a positive number, I can actually go into the lab and I can find what this value is just from this equilibrium equation that I have right here. Okay, this is at equilibrium. There's no dynamics involved. That means that there's no differential equation associated to this thing. The question is, how do I incorporate a differential equation in this? Well, let's look at another scenario. So let's look at the case when I'm not at equilibrium. Maybe I let this thing settle down, and then I walked back into the room, and I pulled the mass down a little bit. And then you can imagine what's going to happen, right? It's going to sort of wiggle back and forth, up and down. So the question is, how do we describe that mathematically? Well, what we're going to do is we're going to introduce another quantity here. So first of all, we have the same two from before. We have little l, the natural length of the spring. Then we have capital L, the length that is going to be the displacement to equilibrium. And then what we will do is we will let u of t, so it's going to depend on time. This is the displacement from equilibrium. So again, remember, this thing might be hanging from the ceiling, and I came in and I pulled it down a little bit, and I let it shoot back up. U of t is describing this displacement from the equilibrium due to me pulling it at time t. Well, here's what we know. We know that the forces on this thing are going to come from Newton's second law. So I've emphasized this before through this lecture series, but most differential equations that we encounter, particularly from physics and engineering problems, are going to be second order. That is, they depend on the acceleration. And that comes from Newton's second law. So here's what Newton tells me. Newton says that the mass times the acceleration of my displacement is equal to, well, the sum of forces that are acting on this thing. So before I write down what this sum of forces is, let's talk about some forces that could be acting on this. So let's start here. So forces. Well, again, the first one we've already seen here, and it could be the gravity. So in this case, this would be the weight, which is equal to mass times gravity. Okay, so that's still there. It's just acting on the mass in exactly the same way. So pulling down, we're using gravity to denote, or we're using the positive direction to denote downwards. That means going in the same direction as gravity. Similarly, we still have a spring tension that we need to account for. So we have the same thing here. We have a spring force, but now it's a little bit different. It's still proportional, so going in the opposite direction of gravity, it is proportional. That's what the K is in here. But now the length that this thing is being stretched from its original, little l, is L plus U. So there's a little more, right? L could be positive or negative depending on, I've drawn this in such a way that U is positive, but you could imagine this thing bouncing up and going above equilibrium as well, which would give you a negative value of U. Okay, let's keep going. We could have another force that's acting on this thing, and it could be damping. So in this case, say FD, and damping affects or is proportional to the velocity of your displacement. So here, gamma is again going to be a positive quantity, just like my spring force. This is going to be pulling me in the upward direction again, so it's sort of pulling against me. And it's pulling against me, sort of the faster I go, the more of a pulling that I get from this thing. So there's all kinds of different ways that damping could be observed in this system. It could be something like air resistance, or maybe you're doing this in some other medium than just air. So for example, you could imagine you're doing this underwater. Well, the faster that thing's going, the more of a push the water resistance is giving you. That's exactly what you're seeing right here. Or if you really wanted to make this crazy, you can imagine doing this in a big tub of honey, right? So it's extremely, extremely viscous. The faster you try to move here, the more the honey is pushing against you. So that gamma would be huge if you were in, say, a big tub of honey. Now, another way that this could sort of present itself is if you were to draw maybe, or if your experiment had some little guide rails to make sure that your mass was only going in the vertical direction, right? There was no left and right displacement here. Well, then this could account for the friction against these guardrails that you've set up here. So that's another way that damping can come in here. The faster you're going, the more velocity you have, the more the friction is going to rub here and it's going to act against you. So there's a lot of different ways that this can come up. I'm just going to encode it by this piece right here. And then the last one is external forces. So we'll look at this later on in the lecture more. But I'm just going to call this capital F of T. So one example of this is maybe the ceiling that I bolted this to. Maybe I have some control over it. So maybe it's not a ceiling, maybe it's just a long bar, and I can shake that thing up and down, right? Well, that would be an external force. That's me acting on this thing in a prescribed manner. And of course, you can imagine if I'm shaking this thing up and down, for example, that's clearly going to travel through the spring and cause a weird action on the mass as well. So those are the four forces that we are going to consider acting on this thing. If we sum them all up, in this case, we are going to get, again, from Newton, mass times acceleration is equal to the sum of forces acting on us. So first one, weight, mass times gravity. Then the second one is the spring force. And then the damping force. And then, I won't put the T in on this side just because it'll make it uglier. And then plus the external force. Okay. So now what we can do is we can rearrange this. And what I want to use is the equilibrium point here. So I know that mg minus KL is equal to 0. mg minus KL. That piece is equal to 0. So I'm going to write this in the way that we've been writing differential equations all along. All of the independent variables, and all of the dependent variables on the left-hand side, so that's all of the u's. So mu double prime Now this comes over, becomes plus Ku. And this comes over, becomes plus gamma U prime. So I get plus gamma U prime plus Ku. And then this is equal to some external forcing F of t. That is my most general equation to describe this mass spring system. Now, what I really want you to notice here is I have constant mass, constant damping coefficient gamma, and constant spring coefficient k. So this is a second order differential equation that is linear. That's fairly obvious. And all of its coefficients are constant. It's a constant coefficient equation. That means that it has a characteristic equation, and that means that we can analyze it. And the last piece of this is that I can turn this into an initial value problem if I know the initial position of this thing. So maybe, if you're thinking of my example, pulling it down and letting it go, how far I pulled it down from equilibrium. And I also need to know its initial velocity, u prime of v0. U prime of 0 is equal to, in my case, v0. I'm just using that to denote the velocity. So this would constitute a well-posed second order differential equation. So here's what we're going to do for the remainder of the lecture. We're going to walk through this differential equation, and we're going to look at a bunch of different cases here to better understand what's happening. And I'm going to slowly build in more pieces as we go through. So the first thing I want to look at is undamped free vibrations. So let's take a look at this. An undamped free vibration. Okay, so what does that actually mean? Undamped means no damping. So that means that I'm not going to consider this term. So I'm going to imagine there is no, say, air resistance, water resistance, honey resistance, friction, whatever that thing happens to represent. We're not including that in the forces. Now, the free vibration part of this comes from the fact that there's no external forces. This thing is a closed system. Nobody is affecting this model. Okay? So the only thing that can happen is that the mass and the spring are sort of bouncing and interacting with themselves, and that alone. Nobody is shaking this thing. There are no external forces being applied here. This is a very, very nice little differential equation. Second order, constant coefficient. The characteristic equation for this thing, so let me write this, mr squared plus k is equal to 0. This gives me r is equal to plus or minus I, the square root of k over m. Okay, so clearly this thing is imaginary. That comes from the fact that k and m are both positive numbers. So again, m, gamma, k always are going to be positive. In the case of gamma, it's going to be non-negative, right? We're allowing for a 0 value there. But this gives purely imaginary roots to our characteristic equation. Now, we know what imaginary roots do, right? We know that they lead to oscillations. Oscillations means sine and cosine. So the general solution of this thing, u of t is c1 cos the square root of k over m t plus c2 sine the square root of k over m t. There's no exponential terms, and that's because there's no real parts here. So let's think about what this means in the context of my mass spring system right here. What does that tell me? Well, these things oscillate forever. Okay, there's no other dynamics taking place here. They never go to 0. All they do is just oscillate. Nice little sine and cosine waves added together. You know, again, they just look like a little sine or cosine wave, up and down. That's it. So what does that mean here? Well, once I put in my initial conditions, if I pull this thing down, U of t is just going up and down forever. So what does the mass do? It just goes up and down forever. Nothing else, right? And now you might be thinking to yourself, well, Jason, I can imagine doing this, right? Maybe I built this in my basement. It's not going to go forever. I know it's not going to go forever, right? Eventually, if I walk away for 2 days and I come back, it's going to settle down. I agree, but we have done this in an extremely idealized setting. Again, we're doing it in a vacuum. There's no air resistance taking place here. It's the air resistance in your basement that you might be doing this that's eventually going to slow it down. We're not accounting for that because we're not accounting for damping. So if you do this in a vacuum with no external forcing, what's going to happen? Just going to go up and down forever. It's going to be a nice little pendulum here. And what you can see is that we can account for the frequency of oscillation. It's essentially the sort of tightness of the spring, that's a spring constant K, divided by the mass of the object. So if the mass is lighter, so if the mass is smaller, then you have a higher frequency and you have a shorter period. So the oscillations are going to happen very, very quickly. Whereas, similarly, if you have a tighter spring, so if K is bigger, then the frequency is going to get larger. And that means that you are going to have long and slow oscillations. That gives you a longer period. So you can see that we can actually derive the sort of expected dynamics out of this thing just by knowing the spring constant and the mass of this thing. Now, of course, maybe you're not really that impressed. Again, you said, Jason, I do not have access to a vacuum, so I clearly cannot run this experiment. But I probably could go on Amazon or eBay and buy myself a spring and maybe, attach some little weight to the bottom of this thing. And so in theory, I could actually do this experiment, right? This is probably a $100 experiment at the very most. That's not what I'm going to see. What I'm going to see is some sort of air resistance in there. So let's look at another case. Let's look at the case of what are called damped free vibrations. Remember, this was an undamped free vibration. Free means no external. Undamped means no damping. So if it's going to be damped but still free, that means I get 1, 2, 3 forces acting on this, but not the fourth. So I get M U double prime plus gamma U prime plus K U is equal to 0. Okay, now I've got, again, a second order differential equation. I still have a characteristic equation. Let's take a look at what that characteristic equation should be. Again, just putting in e to the RT here, nothing fancy, right? We've been doing this so much that you're probably sick of it, if anything. You could probably do this in your sleep. You might even have nightmares about it. But we can still do it. So we can still analyze this thing. So let's take a look. The characteristic equation here is going to be, so let's put it right underneath, mr squared plus gamma r plus k is equal to 0. Okay, so, it's got some annoying variables in here, m, gamma, and k. But other than that, this is a quadratic equation. I've got the quadratic formula to solve this thing. So my two roots are given by negative gamma plus or minus the square root. And now I have gamma squared minus 4m k divided by 2m. Again, that's just the quadratic formula. Replace your a, b, and c by m, gamma, and k respectively, and boom, there it is. That's all that you need. So clearly, some weird things are going to happen here depending on what is going on underneath this square root, right? Remember, this is exactly where we saw a lot of the discrepancies come up when we were analyzing the different cases of our characteristic equation. So let's take a look. First thing first. here's the one that we would be expecting to come out of this. So this would be gamma squared minus 4mk is less than 0. Now, why am I starting with this one? Well, first of all, let's think about what happens as we slowly turn gamma on. Okay, so we're going to fix k and m. All we're trying to do is update the undamped free vibration case from right here. So we can ask ourselves, what happens as we slowly turn on gamma, right? So it slowly comes off 0. Well, minus 4mk is less than 0. So at least for small values of gamma, this thing is going to be negative. That means that I'm going to have an imaginary part, right? Because underneath my square root is going to be negative. And so that gives me a real part of negative gamma over 2m, and an imaginary part of 4mk minus gamma squared. Let's write down what the solution is here. U of t is equal to C1e, now the real part, minus gamma t over 2m, cos, now the imaginary part, 4mk minus gamma squared t. Don't get intimidated by this. I know it looks daunting, but it's not, right? It's just sort of taking care of all of the little variables here, right? But if you put in numbers for these, maybe 1, 2, 3, then you'll see what I'm talking about, right? All of this will work out. So then I have the exponential part here, 2m sine, and then the square root of 4mk minus gamma squared t. And so what's happening here? Okay, let's just analyze this case. Sines and cosines, still getting oscillations, right? But what's happening to those oscillations? They're being sunk, right? They're getting this exponential term multiplied into them. Because gamma and m are positive, this is a negative exponent on the exponential, and that thing is pulling it into 0. So what's happening? We're getting what are called damped oscillations. Now, it shouldn't be a surprise that we call these things damped oscillations because they are due to the damping, right? It's the gamma that's causing this in here. So what do these things actually look like? Well, roughly, they would look something like this. So they are slowly, slowly, slowly decaying oscillations. We can see here that we get this decay in these terms, and that's coming from the exponential. So what does this represent in terms of my spring mass system? Well, now I've got a little bit of air resistance. This is the case where you pull that mass down. Maybe I leave the room. I come back in 2 days and I see that it's balanced at the equilibrium, right? That's what's happening right here, right? That in-between period, it's going down and it's coming up, but not as high as it was before. It's going down, but not as low as it was before. And it's slowly, slowly, slowly wiggling into 0. Remember, u equal to 0 represents us being at equilibrium here. So this thing is being pulled down and then sort of wiggling ourselves in. That's what this wiggling right here is. This tiny, tiny little wiggle that's left is wiggling into 0. It's sort of a death rattle as you go into equilibrium here. Okay, that's one of 3 cases. Now you can imagine, let's just imagine here that we're sort of increasing the damping, right? Well, what's going to happen is if damping gets bigger and bigger, eventually this thing is going to hit 0. This is a continuous function. And so eventually I can make this big enough so that it's equal to 4mk. Let's look at that now. Gamma squared minus 4mk is equal to 0. Now I've got a double root because this whole piece underneath the square root is equal to 0. And so therefore, what I'm getting is a double root to this characteristic equation, which we know very, very well. This leads to u of t is equal to, well, actually, let's use C1 here, sorry, to be consistent. C1 plus C2T E. And now what's happening here? Well, I'm just left with minus gamma over 2m. Remember, this is 0 underneath the square root. So minus gamma t over 2m. Now, what is this guy doing? Well, no more oscillations, no more sines and cosines. So I'm going straight into 0, right? I might get a little bit of a jump here, but in general, you should expect something that looks like this. So because of this t right here, I get a little bit of growth at the beginning, potentially. So you would get something that goes up and then goes like an exponential right into 0. So what's happening here? This is a case where you have a lot of damping. So I pull down my m, it goes, whoa, and then hits right back into the 0 case, right? So again, I pull it down. This initial little burp here is it flying back up in response to me pulling it down, and then it's slowly settling into its equilibrium point. That's what's happening here, right? And this is a perfect balance between damping and the mass and the spring constant. So this is something you probably would not expect to see in reality. But what you would expect to see is the last case, where this thing is positive. Now, this is positive. You get 2 real roots to this equation, right? So let me just write them down. The solution is u of t is equal to c1 e to the, let's do r1t plus c2 e to the r2t. Now, in this case, you can actually show that when this thing in here is positive, both of the roots have to be negative. So that means that this part goes to 0 and this part goes to 0. So this gives us u of t goes to 0 as t goes to infinity. All right, so I don't want to go too much into the depth here of why that's the case. Maybe you should pause the video and try and show this with a nice little inequality. You can show this piece right here is less than gamma, which means that the top is less than 0 in the plus case. But that tells you that you have 2 negative roots. That tells you that u is going to 0. All 3 cases gave us that u is going to 0 as t goes to infinity. So what do we see here? Damping causes us to sort of die out, to peter out. But the amount of damping causes very different ways that we do this. If damping is very, very small, I get to wiggle my way in. Whereas if damping gets bigger, I go straight in, right? So now these are just exponential decays. That's it. There's not even a burp. There's no wiggles. It's just straight in. Think about this last case. Where would I encounter this? Take my bucket of honey. Do the experiment in the bucket of honey. Now you can close your eyes. You can imagine this. Pull the weight down and let it go. What's going to happen? So slow. Right? It's coming so slow. It's just going to fall into the equilibrium. It's not going to go over the equilibrium. It's just going to go in and settle down. That's what you're seeing here. You just get a monotonic decay into 0, and that's because you are so damped. There's so much resistance acting on this thing. Same thing if you put up guardrails on the side of this and they really, really squeeze in, so you have tons and tons and tons of friction that's being generated here. Well, then this thing is just going to really slowly just die off and go into 0. Okay, so now let's look at what happens when we start putting external forcing on these things. Now, unfortunately, understanding all external forces is just too difficult of a task. You have to use variation of parameters to solve that. So we're going to restrict ourselves to a very specific scenario. And this is a very common one that you would find in engineering and physical applications, and that is a periodic forcing. So for example, you can imagine that maybe if your spring mass system is sort of bolted into maybe a board or a rod, you can imagine that there's something sort of lifting and shaking this board or rod at a periodic interval. Okay, so let's take a look at this. Let's do this sort of by example. And again, I don't want to have to use m, gamma, and delta or m, gamma, and k every single time. I'm just going to use real numbers here, make my life a little easier. So let's do 3 cos t. Okay, so this is a perfectly accessible problem to you, having watched the videos leading up to this, right? This is a linear constant coefficient equation. The external forcing here can be handled as we described in the video on non-homogeneous equations and solutions to those equations. We can even include some boundary condition or some initial conditions here. Let's do u of 0 is equal to 2. U prime of 0 is equal to 3. These are somewhat arbitrary, mostly just for exposition, okay? And here's what I want to do. Well, we know that we can sort of go through all of the methods here, and we can get the solution to this thing. So I'm going to skip all of the fun. I'm going to leave this for you as an exercise. But this gives me, let's take a look, u of t is equal to, okay, I got 22 over 17 e to the minus t, and then, t over 2, pardon me, cos, and inside of the cos is just a t term, and now plus 14 over 17 e to the minus t over 2 sine of t, and then plus, so this is the homogeneous solution. The C1s and C2s have already been found using my initial conditions. That's why I gave them. And then let's put the specific part in. So I get plus 12 over 17. And this is going to be sine of t. Remember, the specific part is going to be a constant times sine plus a constant times cos. Identifying those constants is the name of the game. So I got 48 over 17 cosine of t. Okay, now let's take a look at this. Let's sort of examine this out for a moment. What's happening here? Okay, so remember, this is the specific part. It is due particularly to this external forcing, this periodic forcing that's being applied here. This is the homogeneous part. The homogeneous equation is a damped vibration equation, right? It's damped because there's a gamma in here. There's gamma equal to 1. Then you can see, just like we covered in the damped part, these damped oscillations from the homogeneous part are dying out. So let me just write it like this. Going to 0, going to 0. Now I'm taking time to infinity here. That's because of the exponential terms. So what happens after a while? These homogeneous parts, these damped oscillations, they die out, just like they were doing with the last piece down here. What are we left with? Constant periodic motion. And what is that? What is the period of that periodic motion? It's exactly the same as the period of the forcing here. So what's happening? I'm shaking this board up and down. Then I take the weight and or the mass, and I pull it down, I let it fling up and do its thing. Well, initially, from me flinging it, there's a little bit of a transient with this damped oscillation, but eventually the wind resistance kicks in, or the air resistance, the water resistance, whatever it is, the friction kicks in, and it kills that oscillation. But you're still shaking this thing. So eventually, what this does is it synchronizes up with the shaking that's going on up here. So this is sort of like a yo-yo, right? That's exactly what's happening. The periodicity that I am throwing my yo-yo at the ground, the yo-yo is going up and down with that same periodic motion. That's the same thing that's happening with my mass and my spring coming from this external forcing right here. Okay, let's see another example. Let's see what happens if I do this in a vacuum. So I don't put any damping on this. Let's do u double prime plus u is equal to, let's say, cos I'm going to use omega. This is the sort of standard parameter that people use for the frequency. So in this case, omega is a positive number. Basically, you can imagine that I've got a dial on my system here, and I can choose what the frequency I'm going to force this thing with. Okay, that's what my omega is. Okay, well, let's take a look at something right away. So first, if omega does not equal to 1, well, if omega is not equal to 1, then we don't have any problems with the homogeneous equation, right? Because the solutions to the homogeneous equation are cos and sine. And so this gives me solutions that look like this. Now, I'm going to write this in the following way. So I actually get u of t is equal to, now I get C1 cos of t, and then plus C2 sine of t. Sorry, the marker is not cooperating here, so let's do this. Let's go back to green, plus C2 sine of t. And then I have this specific part. You can very easily check that, in fact, only the cosine comes through. And it comes through in the following way. 1 over 1 minus omega squared cos of omega t. Now, you can see where the condition omega not equal to 1 in here comes from, because then I can make sure that I'm not dividing by 0. And so what's going on with this thing? Well, let's take an exposition, okay? So what I want to do is I want to pick specific values of C1 and C2 so that you can see what's going on, okay? Now, this is actually going to hold more generally for any values of C1 and C2, but this is at least going to allow you to sort of understanding what is happening here for omega not equal to 1. So let's take C1 is equal to the negative of this thing. So minus 1 over 1 minus omega squared. And let's take C2 equal to 0. Okay. So in this case, then, u of t becomes 1 over 1 minus omega squared. I can factor that out because that's coming from the C1 now, and it's coming from the specific part. That's why I wanted to choose those in that way. I also wanted to just choose 2 coses. I didn't want to have a sine mixed in there. Now, we know sines and cosines are just the same functions, right? So that's what I mean about different values of C1 and C2 are going to give the same basic results here, but I just want this for exposition. Then I get cos of omega t minus cos of t. Okay, that's, I don't know, maybe it looks a little better to you, but it's still not completely illuminating. Here's what I'm going to do. I'm going to use a trigonometric identity, right? There's a way, there's a trigonometric identity that tells you the difference of cosines. You can write this as the product of sine functions. So in fact, this becomes 2, and then 1 minus omega squared, and then sine, now let's do this properly, 1 minus omega t divided by 2, and then sine 1 plus omega t over 2. Right? So there's 2 frequencies in these sine functions, 1 minus omega and 1 plus omega. Actually, technically it's 1 minus omega over 2 and 1 plus omega over 2. But what does that actually look like? Well, one way to interpret this thing is to think of this as the amplitude of oscillation and to think of this as the envelope of oscillation. So what does this really look like? Well, if I just plot this thing, so let's do that first. That is going to look like Just a nice sine curve, right? Similarly, if I plot the negative of that, so let's maybe put it like this. If I plot the negative, I get this. Now, this is why I called it an envelope, because this thing tells me how big I can be in terms of oscillation. That's assuming this piece is equal to 1, right? Or -1. At the very worst, right, I'm going to get this thing on the tops and bottoms. Now, what that piece right here is giving is it's giving an amplitude modulation, right? The amplitude of this thing is not always 1 or -1. That's the biggest it could possibly be. So what happens is you see that you can only bounce around inside of this little envelope. So this in green here is actually the signal that I'm getting out of this thing. Okay, so it goes all the way up to the envelope edges. Okay, so what's happening is that when this thing is equal to plus or minus 1, it's major in extremes, right? Which is happening quite quickly because of the 1 minus omega being smaller than the 1 plus omega. That's why there's quick little tight oscillations inside of this. It's bouncing between plus or minus 1, which means it's bouncing between the values of this thing. That's why I go all the way up until I hit the envelope, and then all the way down until I hit the envelope, all the way up until I hit the envelope, all the way down. The envelope, remember, is given by the outer function. So if we do sine of 1 plus omega t over 2, right? And this is minus sine of 1 plus omega t over 2. Now, I've completely disregarded the 2 over 1 minus omega squared just because it's not helping us. It's just a number, right? It's just going to stretch or compress this thing. I want you to understand the oscillation that's happening here. This is a modulated oscillation, right? So essentially what's happening is it wants to fall into its own oscillations, but you are forcing it into oscillations that are sort of incommensurate with what it wants to be. And what I mean about that is that it wants to be sine of t and cos of t, just the sort of outer oscillations here. But you're sort of pushing it at something that doesn't sync up with it, right? So you can imagine, you and I are walking side by side. Every time I take 2 steps, you take 2.3 steps or something like that, right? So we're sort of have this weird incommensurate period to our stepping, right? After I take 1 step and 2 steps, you've taken maybe 2.3 steps, right? So we're going to be off. We're not going to be synchronized. That's what we're seeing here. And this is where you're getting this modulation that's coming in right here. Now, the last case here, of course, is what happens when omega is not equal to 1. So let's take a look at that before we wrap up. Sorry, omega equal to 1 now. Well, that means that I'm forcing it at the same frequency that it wants to be at, right? And so now I can get the exact solution out of this thing. And this is going to be u of t is equal to, so c1 cos of t plus c2 sine of t. The homogeneous part never went away. And then I have, well, I'm going to get an A here. I'm going to get an A here. So I get, maybe I'll just call it AT cos of t. Right? So again, you can compute out the A. Again, it's only going to be a cosine that comes through. It's the sort of same thing that we saw right here. But here's the point. I get a T now. All right? I get a T because the homogeneous part is already covered and the forcing is the same as the homogeneous part. So we've seen this before, right? This acts like a repeated root. It means I get a T in here. Now this is interesting, right? Because in this case, I never grew. I was always sort of stuck between, say, -1 and 1. What's happening here? Well, whatever the natural period that this undamped free vibration, so this u double prime plus u falls into, I am forcing it at exactly the same period, right? So every time it goes to its lowest extreme, I am also going to my lowest extreme and I'm pushing it down further. And then every time it comes up to its highest extreme, I am also going to my highest extreme with the forcing and pulling it up even further. So what you're getting is you're getting growth here, right? You're sort of skyrocketing. Now you may have seen this before. If you've ever been on a trampoline with your friend, you get your friend bouncing and they fall into a nice periodic bouncing. Then what you do is you start bouncing beside them. And what you do is you try and synchronize yourselves so that when you come down, your friend comes down and you skyrocket them, right? It's almost like a double jump. Now, if you were able to sort of maintain this, and if, physical restrictions aside, you would be able to bounce them as high as you wanted, right? You could bounce them to the moon just using that synchrony. That's exactly what's happening here. What we see from this is we would see the following. So these things are just going to give oscillations. This gives the growing oscillation, and so you would see something like this. Right? And eventually this thing can be as big as it wants and as small as it wants. You're going to break the system, right? Because this is not possible. It can't just go to plus or minus infinity. Eventually that weight is going to fly off. Maybe it'll go through a window or something like that, or cause some serious damage. And that comes from the fact that you're forcing it at the same frequency that it would prefer to be at. This is what's often referred to as a resonance in physics. And the resonance is denoting the fact that you're forcing at the same period that it already wanted to be in. So you're sort of like double forcing it. You're sort of leapfrogging, and that's where you get this sort of trampoline phenomenon of this double jumps where you can send your friend really high into the area. Okay, that concludes our discussion of second order differential equations. What we're going to do is come back in the next lecture and start talking about higher order equations.